Hello there, and welcome. Tonight I want to take you somewhere special, somewhere that exists in the quiet spaces between what we know and what we can only imagine. Close your eyes for a moment if you'd like, and picture the vastness of space stretching out in all directions from where you are right now. Above you, below you, all around you, the cosmos extends into infinity, filled with mysteries we're only beginning to glimpse. And tonight, we're going to explore one of the most intriguing questions that has emerged from our study of the heavens. What if the universe has been sending us visitors all along, and we simply couldn't see them until now? It's a question that might initially sound like science fiction, something from the realm of imagination rather than serious scientific inquiry. But consider this. In all the billions of years that our solar system has existed, spinning quietly in one arm of the Milky Way galaxy, we've only had the technology to detect faint, fast-moving objects from beyond our sun's influence for a few decades. That's like having eyes for just the last second of a day that began at midnight. What might we have missed in all those hours of darkness? What cosmic wanderers might have passed by Earth, silent and invisible, carrying secrets from distant stars? Perhaps you've heard of Three-Eye Atlas, though, maybe not by that name. You might know it as the third confirmed interstellar object to visit our solar system, discovered in 2024 by the Atlas telescope system in Hawaii. But here's where our story takes a fascinating turn, where scientific observation meets cosmic mystery. What if Three-Eye Atlas, and objects like it, have always been passing through our neighborhood, drifting between the planets like ghost ships in the night, visible only when we finally developed eyes sensitive enough to see them? What if the universe has been far more connected, far more alive with wandering voyagers than we ever imagined? As you settle in tonight, letting the weight of the day slip away, I want to share with you a story that unfolds across impossible distances and incomprehensible timescales. It's a story about how we discovered that we're not as isolated as we once thought, that our solar system isn't a closed bubble, but rather a port of call for ancient travelers from across the galaxy. These visitors don't arrive with fanfare or bright lights. They come quietly, almost invisibly, requiring our most sensitive instruments and our most careful observations to detect them at all. The discovery of Three-Eye Atlas wasn't a moment of dramatic revelation. There was no eureka moment, no scientist jumping up from their desk in excitement. Instead, it was a gradual realization, emerging from careful analysis of data collected by automated telescopes that scan the sky each night, searching for anything that moves against the fixed backdrop of stars. These telescopes, part of the Asteroid Terrestrial Impact Last Alert system, were actually designed to protect Earth from potentially hazardous asteroids. But in their vigilant watch, they've become witnesses to something far more profound: the regular passage of objects that don't belong to our solar system at all. Think about that for a moment. We built these electronic eyes to watch for danger, and instead, they've revealed that we're part of a vast cosmic exchange program, where material flows between star systems like seeds carried on an infinite wind. The Atlas system consists of 4 telescopes, each one modest in size but powerful in capability, scanning the sky multiple times each night. They work while we sleep, taking image after image, comparing them to find anything that has moved. Most of what they find are asteroids and comets that have always belonged to our solar system, objects that have been circling our sun since the planets themselves formed. But occasionally, very occasionally, they spot something different. The mathematics of detection are humbling when you really consider them. Space is so vast, so empty, and these interstellar visitors are so small and dark that finding them requires an almost impossible combination of factors. First, the object has to pass close enough to Earth to be visible to our telescopes. Not too close. Mind you, we're talking about distances of millions of miles, but close enough that the faint sunlight reflecting off its surface can travel all the way to our instruments. Second, it has to be moving at just the right angle for us to notice its unusual trajectory. And third, we have to be looking in exactly the right place at exactly the right time. When you think about all these requirements, the fact that we found any interstellar objects at all seems miraculous. And this brings us to the heart of tonight's contemplation. If we found 3 confirmed interstellar visitors in just the past few years, after having the capability to detect them for only a few decades, how many must have passed by unnoticed throughout Earth's history? How many are passing by right now, too faint or too distant for our current technology to detect? The story of how we recognize 3i Atlas as an interstellar visitor is itself a testament to human ingenuity and patience. When the Atlas telescopes first spotted it, it appeared as nothing more than a faint point of light, barely distinguishable from the cosmic background. But as astronomers tracked its movement night after night, something unusual emerged. Its path through space didn't match any orbit that would keep it bound to our sun. Instead, it was following what we call a hyperbolic trajectory, a path that would take it into our solar system once, and then fling it back out into interstellar space, never to return. This hyperbolic path is like a signature, a calling card that immediately identifies an object as a visitor from beyond. Objects that belong to our solar system move in closed loops, ellipses that might be stretched and elongated, but always closed, always bringing the object back to where it started. But interstellar visitors move on open paths, curves that sweep in from infinity and return to infinity, passing through our solar system just once in their eternal journey through the galaxy. As we've gotten better at detecting these objects, we've begun to realize something profound about the nature of our cosmic neighborhood. The space between stars, which we once thought of as empty and isolating, is actually crisscrossed with the paths of countless wandering objects. Some are tiny grains of dust, others are mountain-sized chunks of rock and ice, and perhaps some are even larger, planet-sized bodies that drift through the darkness too far from any star to be seen. Our solar system, rather than being an isolated island, is more like a house beside a busy but invisible highway, with traffic passing by constantly, most of it unnoticed. The name 3i Atlas itself tells a story. The 3i designation means it's the 3rd confirmed interstellar object we've discovered, following Oumuamua in 2017 and Borisov in 2019. Each of these discoveries has expanded our understanding of how common these visitors might be. When Oumuamua was first discovered, some scientists thought it might be a once-in-a-lifetime event, a rare cosmic coincidence. But then came Borisov, and then 3i Atlas, and now we're beginning to understand that these objects aren't rare at all. They're simply hard to see. Consider the profound shift in perspective this represents. For all of human history, we've looked up at the night sky and seen it as distant and untouchable, separated from us by an unbridgeable void. But now we know that pieces of those distant star systems regularly pass through our own solar system. The atoms that make up these interstellar visitors were forged in alien suns, perhaps billions of years ago. They've traveled distances that our minds can barely comprehend, carrying with them information about parts of the galaxy we'll never directly explore. What makes 3i Atlas particularly intriguing is how ordinary it appears to be. Unlike Oumuamua, which had an unusual elongated shape that sparked all sorts of speculation, 3i Atlas seems to be a fairly typical comet, similar in many ways to the comets that belong to our own solar system. It has a nucleus of rock and ice, and as it approached the Sun, it developed the characteristic tail that we associate with comets. But this ordinariness is perhaps the most extraordinary thing about it. It suggests that the processes that form comets around our Sun are universal, that throughout the galaxy, similar objects are being created and then scattered into interstellar space. The journey that brought 3i Atlas to our solar system likely began billions of years ago, in the chaotic early days of another star system's formation. Perhaps it formed in a disk of dust and gas around a young star, similar to how our own solar system's comets formed. But instead of settling into a stable orbit, it was gravitationally ejected, flung out into the darkness between stars. Since then, it has been drifting through space, a lonely voyager carrying the chemical fingerprints of its home system. During its long journey through interstellar space, 3I Atlas would have experienced conditions we can barely imagine. The temperature would have been just a few degrees above absolute zero, cold enough to freeze even hydrogen. There would have been no sunlight, no warmth, just the faint glow of distant stars and the even fainter cosmic microwave background radiation left over from the Big Bang. For millions or billions of years, it drifted in this cosmic deep freeze, unchanged and unchanging, a piece of another star system preserved in the ultimate time capsule. And then, after eons of darkness and cold, 3I Atlas began to feel the gentle tug of our sun's gravity. At first, the effect would have been almost imperceptible, just the slightest deviation from its straight-line path through space. But as it drew closer, the sun's influence grew stronger, pulling it into our solar system. For the first time in perhaps billions of years, it felt warmth. The ices that had been frozen solid since before Earth existed began to sublimate, turning directly from solid to gas, creating the glowing tail that would eventually allow us to spot it. This is where our ability to detect objects like 3I Atlas becomes crucial to our story. The tail of a comet, that beautiful glowing stream that trails behind it, is only visible when the comet is relatively close to a star. In the vast spaces between stars, these objects are dark and invisible, reflecting no light, emitting no energy that we could detect. They become visible to us only during their brief passage through the inner solar system, when the sun's heat activates them. It's like they emerge from invisibility for just a moment before disappearing back into the darkness. The timing of our technological development and the discovery of these objects is particularly thought-provoking. We developed the ability to detect faint, fast-moving objects in space, just as we also developed computers powerful enough to calculate their orbits and determine their origins. If 3I Atlas had passed through our solar system just a century ago, we would have missed it entirely. And this raises the question, how many similar objects passed by during the age of the dinosaurs, during the formation of Earth itself? The answer, based on our current understanding, is probably millions, perhaps billions. Current estimates suggest that at any given moment, there might be thousands of interstellar objects within the orbit of Neptune, and several within the orbit of Earth. Most of them are too small and too dark for us to see with our current technology. They're like cosmic ghosts, present but invisible, passing through our solar system without leaving any trace we can detect. 3I Atlas and its discovered companions are just the tip of an enormous iceberg, the few objects large enough and close enough and bright enough for us to spot. This hidden population of interstellar visitors has profound implications for our understanding of planetary systems and the exchange of material between them. Every star system, it seems, is constantly shedding objects into interstellar space. Gravitational interactions between planets, close encounters with other stars, and the chaotic dynamics of planetary formation all contribute to ejecting objects from their birth systems. These ejected objects then wander the galaxy, occasionally passing through other star systems, creating a vast network of material exchange that we're only beginning to appreciate. Some scientists have suggested that this exchange of material between star systems could have important implications for the spread of organic molecules or even life itself through the galaxy. While 3I Atlas itself is unlikely to harbour life, the conditions in interstellar space are far too harsh. It might carry organic molecules, the building blocks of life, from one star system to another. This idea, known as panspermia, suggests that life might spread through the galaxy like seeds on the wind, with interstellar objects serving as the vectors of transmission. The discovery of 3I Atlas also tells us something important about the future of astronomy and our ability to detect these cosmic visitors. As our telescopes become more sensitive and our surveys more comprehensive, we'll undoubtedly discover more interstellar objects. Each discovery will add to our understanding of how common these objects are, and what they can tell us about other star systems. We're at the beginning of a new era of astronomy, one where we can study pieces of other star systems without having to travel to them. Future telescopes already being planned and built will be able to detect much fainter objects than we can see today. The Vera Rubin Observatory, for example, will survey the entire visible sky every few nights, creating a movie of the cosmos that will reveal countless moving objects. Many of these will undoubtedly be interstellar visitors, objects that have been passing through our solar system all along, but were too faint for us to see. Each discovery will be like finding a message in a bottle, cast into the cosmic ocean by a distant star system billions of years ago. As you drift deeper into relaxation tonight, consider the beautiful symmetry of this cosmic exchange. Just as our solar system receives visitors from other star systems, it also sends its own objects out into interstellar space. Comets and asteroids that get too close to Jupiter or the other giant planets can be gravitationally ejected, flung out of our solar system to begin their own eternal journey through the galaxy. Perhaps, billions of years from now, one of these objects will pass through an alien solar system, where it might be detected by whatever intelligent beings have evolved there. They'll study it just as we study 3i Atlas, trying to understand what it tells them about our sun and the planets that orbit it. This reciprocal exchange creates a kind of cosmic community, a slow-motion conversation between star systems that unfolds over billions of years. We're all sharing material, sending pieces of ourselves out into the galaxy and receiving pieces of other systems in return. It's a process that has been going on since the first stars formed, creating an intricate web of connections that spans the entire galaxy. 3i Atlas is just one thread in this vast tapestry, but by studying it, we're learning to see the entire pattern. The question that gives our story its title, was 3i Atlas always invisible until now, has both a simple answer and a profound one. Simply put, yes, objects like 3i Atlas have been passing through our solar system throughout its history, invisible to any observers who might have been watching. But more profoundly, the question asks us to consider what else might be invisible to us right now, what other cosmic phenomena we lack the technology or the perspective to see. Perhaps there are entire categories of objects passing through our solar system that we can't detect with our current instruments. Dark objects that don't develop cometary tails, or objects so small that they're below our detection threshold, or objects moving so fast that they pass through before we can spot them. The discovery of 3i Atlas and its companions has shown us that the universe is far more dynamic and interconnected than we imagined, but it has also reminded us of how much we still don't know. As we continue to watch the skies, developing better instruments and more sophisticated analysis techniques, we'll undoubtedly discover more interstellar visitors. Each one will tell us something new about the galaxy we inhabit, about the processes that shape planetary systems, and about our own place in the cosmic order. But perhaps more importantly, each discovery will remind us of the vast invisible realm that surrounds us, the countless objects and phenomena that exist beyond our current ability to perceive them. The story of 3i Atlas is ultimately a story about the expansion of human awareness, about how we're gradually learning to see things that have always been there, but were hidden from us. It's a humbling reminder that our picture of the universe is always incomplete, always evolving as we develop new ways of looking and new ways of understanding what we see. The invisible becomes visible, the unknown becomes known. But there's always more darkness beyond the edge of our perception, always more mysteries waiting to be discovered. Tonight, as you rest, imagine yourself as part of this cosmic exchange. The atoms in your body were forged in the hearts of stars, scattered into space when those stars died, and eventually incorporated into the Earth when our solar system formed. You are, in a very real sense, made of stardust, connected to the entire cosmos through the material that makes you up. And just as you're made of material from across the galaxy, pieces of our solar system are even now journeying to distant stars, carrying with them the story of our sun and its planets. 3i Atlas will continue its journey long after we've stopped watching it. it will sail back out into interstellar space, returning to the cold and darkness that has been its home for billions of years. But its brief passage through our solar system has changed us. It has shown us that we're not alone, not isolated, but part of a vast cosmic community where material and perhaps information flows freely between the stars. It has revealed to us the invisible threads that connect all star systems, the hidden highways that crisscross the galaxy. In the coming years and decades, as we discover more interstellar visitors, we'll build up a catalogue of these cosmic wanderers. Each one will be unique, carrying information about its home system and its journey through space. Some might be ancient, formed in the early days of the galaxy when the first stars were still young. Others might be relatively recent escapees, ejected from their home systems just millions of years ago. Together, they'll help us piece together a picture of how planetary systems form and evolve, how material moves through the galaxy, and how common or rare our own solar system might be. The search for interstellar objects like 3I Atlas is also changing how we think about the search for life in the universe. If material can move between star systems, then perhaps life, or at least the chemical precursors to life, can as well. Every interstellar visitor is a potential carrier of organic molecules, a possible seed for life in whatever system it passes through. While the chances of any individual object carrying life are vanishingly small, the sheer number of objects moving between star systems means that over billions of years, the probability of life-bearing material being exchanged becomes significant. This perspective transforms our view of the galaxy from a collection of isolated star systems to a connected network where material, energy, and perhaps even life can flow from one system to another. We're not islands in an empty ocean, but nodes in a vast web, connected to every other star system through these wandering ambassadors. 3 Atlas is proof of these connections, a tangible piece of another star system that we can observe and study. As our technology continues to improve, we might one day be able to send spacecraft to intercept and study these interstellar visitors up close. Imagine a future mission that could rendezvous with an object like 3I Atlas, landing on its surface to directly sample material from another star system. Such a mission would be like traveling to another star without actually leaving our solar system, bringing us samples of alien geology and chemistry that we could study in detail. The technical challenges of such a mission would be enormous. Interstellar objects move through our solar system at tremendous speeds, and matching velocities with them would require spacecraft far more capable than anything we've built so far. But the scientific payoff would be equally enormous. Direct samples from another star system would tell us about the conditions there in ways that no telescope observation ever could. We could study the isotopic ratios of the elements, looking for signatures of the nuclear processes in the star that created them. We could search for organic molecules, or even signs of past or present life. Until that future day when we can directly study these objects, we'll continue to observe them from Earth, extracting as much information as we can from the light they reflect and emit. Every spectrum we collect, every image we take, adds to our understanding of these cosmic visitors and what they tell us about the galaxy we inhabit. 3I Atlas, during its brief appearance in our skies, has already taught us so much about the nature of interstellar objects and the frequency with which they visit us. The philosophical implications of these discoveries are as profound as the scientific ones. For all of human history, we've wondered whether we're alone in the universe, whether Earth is unique or one of many living worlds. The discovery of interstellar objects doesn't answer this question directly, but it does show us that the universe is more interconnected than we imagined. If material can move between star systems, then perhaps life can too. Perhaps we're part of a vast cosmic ecosystem that we're only beginning to perceive. Consider too the temporal aspects of this cosmic exchange. 3I Atlas might have been traveling through space since before our solar system even existed. It carries with it a record of conditions in the early galaxy, a time capsule from an era we can never directly observe. By studying objects like it, We're not just learning about other places in the galaxy, we're learning about other times as well. Each interstellar visitor is a messenger from both a distant place and a distant time, bringing us information that no other source could provide. The darkness of space, which once seemed like a barrier separating us from the rest of the universe, is now revealed to be full of invisible travelers, each one carrying stories from across the galaxy. We're surrounded by these cosmic messengers, most of them too small or too dark for us to see, but all of them part of the vast exchange of material that connects every star system to every other. 3 Atlas happened to pass close enough and bright enough for us to spot it, but it represents countless others that remain invisible, passing through our solar system like ghosts in the night. As you continue to relax, letting these thoughts wash over you like gentle waves, consider how the story of 3 Atlas changes our perspective on our place in the universe. We're not isolated observers, watching the cosmos from afar. We're active participants in a galactic exchange program that has been running for billions of years. Our solar system is both a sender and receiver of cosmic messages, written not in words but in the physical material of comets and asteroids. The discovery that objects like 3I Atlas have always been passing through our solar system, invisible until we develop the technology to see them, is a reminder of how much our perspective can change with new tools and new understanding. What seems empty and static from one viewpoint can be revealed to be full of activity and connection from another. The universe hasn't changed, our ability to perceive it has, and as our perception continues to expand, who knows what other invisible phenomena we'll discover, what other connections we'll uncover. Perhaps one day we'll look back on this era, when we first discovered interstellar visitors, as a turning point in human understanding, the moment when we realized that the boundaries between star systems are more porous than we imagined. 3I Atlas and its companions are the harbingers of this new understanding, the first drops of rain that signal an approaching storm of discovery. As we get better at finding and studying these objects, we'll build up a new picture of our galaxy, one where material flows freely between stars, where every system is connected to every other through a vast network of wandering objects. The question of whether 3I Atlas was always invisible until now thus becomes a metaphor for all the things we don't yet know, all the phenomena that surround us but remain hidden from our current perception. It reminds us to approach the universe with humility and wonder, knowing that there's always more to discover, always another layer of reality waiting to be revealed. The cosmos is full of invisible wonders, and we're just beginning to develop the eyes to see them. Before I share something special with you, let me tell you about how you can continue this cosmic journey with me. If you're finding peace and wonder in these contemplations about our universe, if the mysteries of space help you drift into restful sleep, while keeping your mind gently engaged, there's so much more we can explore together. You can find more of these soothing space documentaries on our channel, each one carefully crafted to blend scientific wonder with peaceful narration. Simply subscribe and tap the notification bell, and you'll never miss a journey into the cosmos. We release new documentaries regularly, each one exploring different mysteries of space in this same gentle, contemplative style. Whether it's the hidden oceans of distant moons, the secret lives of galaxies, or the invisible forces shaping our universe, we're here to guide you through the wonders of space as you drift off to sleep. Your support helps us create more of these peaceful explorations, and we'd love to have you join our community of cosmic dreamers. Now let's continue our journey into the hidden ballet of space. As we drift deeper into the cosmic night together, let me paint for you a picture of space that might surprise you. We often imagine the void between stars as empty, a perfect vacuum where nothing exists and nothing happens. But what if I told you that right now, as you rest comfortably, thousands upon thousands of invisible objects are performing an elaborate dance all around our solar system? What if the darkness we perceive when we look up at the night sky is actually alive with movement, filled with cosmic wanderers tracing elaborate paths we simply cannot see? This hidden ballet has been performing since the birth of our galaxy, an endless choreography of objects moving through space, influenced by the gentle pull of gravity from stars and planets they pass. Most of these dances remain forever invisible to us, too small, too dark, too distant for our instruments to detect. They glide through the cosmic darkness like phantoms, their presence known only through the subtle gravitational influences they might have on the objects we can see, or through the rare occasions when one of them, like Three-Eye Atlas, passes close enough to our sun to briefly become visible. Imagine, if you will, standing in a vast dark theatre where a ballet is being performed. The stage is so enormous that you can't see its edges, and most of the dancers are dressed in black, invisible against the dark backdrop. Only occasionally does one dancer move into a small pool of light at the centre of the stage, our solar system, where you can briefly glimpse their movement before they disappear back into the darkness. This is what's happening in space around us all the time. We're watching a performance where we can only see the tiniest fraction of the performers, and only for the briefest moments. The scale of this hidden dance is almost impossible for our minds to truly grasp. Within just the orbit of Neptune, the outermost major planet in our solar system, there might be thousands of interstellar objects at any given moment. Each one is following its own unique path, determined by its velocity and the gravitational pull of our sun and planets. Some are just passing through, their paths barely curved by our sun's gravity. Others are taking more elaborate routes, looping around the sun before heading back out into interstellar space. And all of this is happening in complete silence and near complete darkness. These cosmic dancers come in all sizes, from tiny grains of dust no bigger than a speck of sand to massive objects that might be kilometers or even tens of kilometers across. The smallest ones, the dust grains, are by far the most numerous. There might be trillions of them passing through our solar system right now, each one a tiny piece of another star system, carrying with it information about its place of origin. But these smallest dancers are also the most invisible, far too tiny for our telescopes to detect individually. And we only know they're there through indirect evidence, through the faint glow they create when they collide with other particles, or when millions of them together scatter sunlight in ways we can measure. The medium-sized dancers, objects ranging from pebbles to boulders to mountains, make up the next tier of this cosmic ballet. These are still far too numerous for us to count, and most are too small and dark for us to see. But occasionally, when one passes close enough to Earth and happens to reflect sunlight at just the right angle, we catch a glimpse of it. These glimpses are like seeing a single dancer's hand briefly enter the spotlight before disappearing again, enough to know they're there, but not enough to follow their full performance. And then there are the star performers, the objects like Three-Eye Atlas that are large enough and pass close enough for us to track for weeks or months. These are the dancers we can actually watch, following their movements as they sweep through our solar system. But even these visible performers represent just a tiny fraction of the total population. For every Three-Eye Atlas we detect, there might be thousands or millions of smaller objects following similar paths that we simply cannot see. The paths these objects follow through space are determined by the laws of physics, specifically by gravity and momentum. Each object enters our solar system with a certain velocity and direction, what astronomers call its velocity vector. As it approaches our sun, gravity begins to bend its path, pulling it into a curve. The shape of this curve depends on how fast the object is moving and how close it comes to the sun. Objects moving very fast might have their paths barely bent at all, while slower objects might be pulled into dramatic hairpin turns before being flung back out into space. What makes this cosmic choreography particularly beautiful is that no two objects follow exactly the same path. Each one has its own unique trajectory, determined by its individual speed, direction, and the precise gravitational influences it encounters. Even objects that enter our solar system from the same direction and at similar speeds will follow slightly different paths, influenced by the positions of the planets at the time of their passage. Jupiter, with its enormous mass, acts like a cosmic choreographer, significantly altering the paths of objects that pass near it. Saturn, Uranus, and Neptune play similar but smaller roles, each adding their own gravitational influence to the dance. The timescales of this ballet are as mind-bending as its spatial scales. An object like 3i Atlas might take several years to cross our solar system, moving at speeds of tens of kilometers per second. But its journey to reach us might have taken millions or billions of years. During that vast span of time, it was performing a different kind of dance, a slow drift through interstellar space, its path influenced by the combined gravity of all the stars in our galaxy. This interstellar phase of the dance is so slow that the object might appear almost motionless, drifting through space at a pace that would make a snail seem fast by comparison. Yet even this apparently slow drift is actually quite fast when you consider the distances involved. An interstellar object moving at just a few kilometers per second, slow by cosmic standards, is still covering distances that dwarf anything on Earth. In a single day, it might travel millions of kilometers, farther than any human has ever journeyed. In a year, it could cover distances comparable to the orbit of Earth around the Sun. And over millions of years, these seemingly slow speeds add up to journeys spanning light years. The hidden nature of this cosmic ballet raises profound questions about what else might be happening in space that we cannot perceive. If thousands of interstellar objects are passing through our solar system invisibly, what other phenomena might be occurring all around us without our knowledge? Perhaps there are entirely different types of cosmic dances that we haven't even imagined yet, following patterns and rules we don't understand. The discovery of the first interstellar objects has opened our eyes to one previously hidden aspect of cosmic activity, but it has also reminded us of how much might still remain hidden. Consider the possibility that some of these invisible dancers might be carrying more than just rock and ice. What if some of them harbour complex organic molecules, the building blocks of life? Or what if, in the vast population of interstellar objects, there are some that were once part of living worlds, carrying fossilised remains of alien life forms? These possibilities transform the hidden ballet from a purely physical phenomenon into something potentially biological, a cosmic exchange of the ingredients, or even the remnants of life. The darkness of space, which seems so empty when we look at it with our eyes, is thus revealed to be full of activity and possibility. It's like looking at the ocean at night. The surface might appear calm and featureless, but beneath it, countless creatures are moving, hunting, feeding, living their lives completely invisible to us. Space is the same way, full of objects and activities that remain hidden simply because we lack the ability to see them. 3i Atlas briefly emerged from this hidden realm, like a deep-sea creature briefly surfacing, giving us a glimpse of the vast invisible population that surrounds us. The technology we use to detect these cosmic dancers is itself a marvel of human ingenuity. Modern telescopes don't just take single images, they take thousands of images of the same patches of sky, comparing them to detect anything that moves. Sophisticated computer algorithms analyze these images, looking for the telltale signs of an object moving against the background stars. It's like trying to spot dancers in a dark room by taking thousands of photographs with a very dim flash, then comparing all the photos to see what has changed position. But even our best technology can only reveal a tiny fraction of the cosmic ballet. We can only detect objects that are large enough, bright enough, and close enough to register on our instruments. This creates what astronomers call a selection bias. We're only seeing the biggest, brightest dancers who come closest to the spotlight. The vast majority of the performance remains hidden in darkness, invisible to even our most sensitive instruments. This limitation has led scientists to develop statistical models to estimate the true population of interstellar objects. Based on the few we've detected, they calculate how many more must be out there that we cannot see. These calculations suggest numbers that boggle the mind, potentially millions of interstellar objects within our solar system at any given moment, with new ones constantly arriving and others departing. Our solar system isn't an isolated stage, but rather a busy intersection, where countless cosmic paths cross. The gravitational interactions between these invisible objects and the planets of our solar system create subtle perturbations, tiny changes in orbits that accumulate over millions of years. While any individual object has a negligible effect, the cumulative influence of millions of them passing through over billions of years might have played a role in shaping the current architecture of our solar system. The planets themselves might have been nudged into their current orbits partly by the gentle gravitational tugs of countless invisible visitors. Some of these cosmic dancers might occasionally collide with planets or moons, delivering material from other star systems directly to their surfaces. Earth itself has probably been struck by interstellar objects many times throughout its history, though distinguishing these impacts from those of local asteroids and comets is nearly impossible. Each impact would have delivered alien material to our planet, adding ingredients from other star systems to Earth's geological and perhaps biological evolution. The idea that Earth has been receiving material from other star systems throughout its history adds another layer to our understanding of our planet's story. We're not just a product of our own solar system, but have been influenced and enriched by material from across the galaxy. Every interstellar impact, no matter how small, has contributed something unique to our world, making Earth a cosmic collection point for material from throughout the galaxy. As we observe more of these cosmic dancers, patterns are beginning to emerge. Scientists have noticed that interstellar objects seem to come from certain directions more often than others, suggesting that there might be preferred paths through our galaxy, cosmic highways where objects are more likely to travel. These patterns might reflect the overall rotation of our galaxy, the distribution of stars in our neighborhood, or the aftermath of ancient stellar encounters that scattered objects in particular directions. The study of these patterns is revealing the hidden structure of our galaxy, the invisible currents and flows that guide objects through interstellar space. Just as ocean currents guide ships and marine life along preferred routes, these cosmic currents might channel interstellar objects along particular paths. Our solar system sits at the intersection of several of these cosmic currents, making it a natural gathering point for objects from across the galaxy. The dance of interstellar objects through our solar system is also teaching us about the life cycles of planetary systems throughout the galaxy. Every star system, it seems, goes through phases where it ejects large amounts of material into interstellar space. Young systems, still in the process of forming planets, are particularly prolific, scattering debris in all directions as planets grow and migrate. Older systems continue to eject objects through gravitational interactions between planets and smaller bodies, and dying systems, where stars are expanding or exploding, release vast amounts of material into space. This constant exchange of material between star systems means that the galaxy is more interconnected than we ever imagined. It's not a collection of isolated systems, but rather a vast network where material constantly flows from one system to another. The atoms that make up 3i Atlas might have been part of multiple star systems before beginning their current journey, and they'll likely become part of other systems in the future. The cosmic ballet is thus not just a dance of individual objects, but a grand exchange of material that has been going on since the galaxy formed. The invisible dancers passing through our solar system right now carry with them stories from across the galaxy and throughout cosmic history. Some might be ancient, formed in the first generation of stars that lit up after the Big Bang. Others might be relatively young, ejected from star systems that formed just millions of years ago. Each one is a time capsule, preserving information about the conditions in which it formed and the journey it has taken since then. If we could see all these invisible objects, the night sky would look completely different. Instead of appearing mostly empty with scattered points of light, it would be alive with movement, filled with objects tracing paths in all directions. It would be like watching a time-lapse video of a busy city at night, with countless lights moving along streets and highways, each one following its own path but all contributing to the overall flow of traffic. the cosmic ballet would be revealed in all its complexity and beauty. The discovery that this ballet has been performing around us all along, invisible to our eyes and instruments, is both humbling and inspiring. It reminds us that our perception of reality is always limited, always incomplete. What appears to be empty space is actually full of activity. What seems to be isolation is actually connection. What looks like stillness is actually constant motion. The universe is far more dynamic and interconnected than our senses can perceive. As our technology improves and we discover more of these cosmic dances, we're gradually learning to see the performance that has been going on around us all along. Each new detection adds another dancer to our awareness, another thread to the cosmic tapestry we're trying to understand. Through Atlas was just one performer in this vast ballet, briefly visible as it passed through our cosmic spotlight before disappearing back into the darkness. The hidden ballet of space continues whether we observe it or not, a perpetual performance that has been going on for billions of years and will continue for billions more. Objects are entering our solar system right now at this very moment, following paths that will bring them close to our sun before sending them back out into the darkness. Most of them we'll never detect, never know about. They'll pass by invisibly, their presence known only to the universe itself. This cosmic dance connects every star system to every other, creating a galaxy-wide choreography of such complexity that we can only glimpse tiny fragments of it. Yet even these glimpses are enough to transform our understanding of our place in the cosmos. We're not isolated observers, but participants in this dance, our solar system both a stage and a dancer, receiving and sending objects in an eternal cosmic exchange. The darkness between stars, rather than being empty and still, is revealed to be full of movement and connection. It's a vast dance floor where countless objects perform their silent ballet, most of them forever invisible to us, but all of them part of the grand cosmic performance. The discovery of 3 Atlas and its companions has given us our first glimpse of this hidden ballet, but it has also shown us how much of the performance remains unseen, how many dancers remain invisible in the cosmic dark. As you rest tonight, imagine yourself surrounded by this invisible dance, these countless objects moving silently through space all around us. You're at the center of a cosmic performance that stretches across the galaxy and spans billions of years. The dancers are out there right now, following their ancient paths, carrying their secrets from star to star. Most of them we'll never see, but knowing they're there transforms our understanding of the space around us. The darkness is not empty but full, not still but constantly in motion, not isolated but connected through the endless dance of invisible cosmic wanderers. There's something almost magical about the way objects can hide in plain sight in space, existing all around us yet remaining completely invisible to our most sophisticated instruments. As we settle deeper into our cosmic contemplation tonight, let's explore the delicate mathematics that governs what we can and cannot see in the vast darkness above us. It's a story of light and shadow, of distance and detection, of how the universe keeps most of its secrets hidden, not through any deliberate concealment, but simply through the fundamental physics of visibility itself. Consider for a moment what it actually means to see something in space. Here on Earth, we're accustomed to seeing objects because they are illuminated by sunlight or artificial light, and that light bounces off them and into our eyes. The same principle applies in space, but the distances involved transform this simple process into something far more challenging. An object like 3i Atlas becomes visible to us only when several mathematical conditions align perfectly, creating a narrow window of detectability in an otherwise invisible journey that might span billions of years. The first and perhaps most fundamental factor in this cosmic hide-and-seek is the inverse square law of light. This elegant mathematical principle states that the intensity of light decreases with the square of the distance from its source. If you double your distance from a light source, the light becomes not half as bright, but 1/4 as bright. Triple the distance, and the light drops to 1/9 of its original intensity. This law governs everything we see in space, from the nearest planets to the most distant galaxies, and it's the primary reason why most objects in our solar system remain invisible to us. Let's apply this principle to an interstellar visitor like 3I Atlas. When it's far from our Sun, perhaps out beyond the orbit of Neptune, the sunlight reaching it is already incredibly faint, about 1,000 times dimmer than the sunlight we experience on Earth. But that's just the beginning of the challenge. That faint sunlight must then reflect off the object's surface and travel all the way back to our telescopes on Earth. By the time this twice diminished light reaches us, it might be billions or even trillions of times fainter than what our eyes could possibly detect. The mathematics becomes even more challenging when we consider the size of these objects. The amount of light an object can reflect depends on its surface area, which increases with the square of its radius. A small object, perhaps just a few meters across, has such a tiny surface area that even if it were perfectly reflective, which it isn't, it would reflect so little sunlight that detecting it would be virtually impossible beyond a certain distance. This creates what astronomers call a detection threshold, a mathematical boundary beyond which objects of a certain size simply cannot be seen, no matter how hard we look. The reflectivity of an object, what astronomers call its albedo, adds another layer to this mathematical invisibility. Most asteroids and comets are quite dark, reflecting only a small percentage of the sunlight that hits them. 3I Atlas, like many comets, might have an albedo of just a few percent, meaning it absorbs more than 95% of the sunlight that reaches it. This dark surface makes it even harder to detect, requiring our instruments to search for an extremely faint signal against the background noise of space. But here's where the mathematics becomes truly fascinating. The background of space itself isn't perfectly dark. There's a faint glow from distant stars, galaxies, and the zodiacal light, sunlight scattered by dust in our solar system. This creates what we might call a noise floor, a minimum level of light that's always present. For an object to be detectable, it must be bright enough to stand out above this noise floor. It's like trying to hear a whisper in a room with a loud air conditioner. The whisper might be there, but if it's not loud enough to rise above the background noise, it remains undetectable. The motion of these objects adds yet another mathematical dimension to their invisibility. Interstellar objects move through our solar system at tremendous speeds, often tens of kilometers per second. This means they don't stay in one place long enough for our telescopes to build up a clear image. In the time it takes to capture enough light to detect a faint object, it might have already moved to a different part of the sky. This creates a fundamental trade-off. We can look deeply at one spot to find very faint objects, or we can survey large areas quickly to catch fast-moving objects, but we can't do both simultaneously. Modern telescopes try to balance this trade-off through sophisticated observation strategies. They take multiple images of the same region of sky, separated by carefully calculated time intervals. By comparing these images, they can detect objects that have moved between exposures. But this technique has its own mathematical limitations. If an object is moving too fast, it might appear as just a streak rather than a point, making it harder to distinguish from cosmic rays or other artifacts. If it's moving too slowly, it might not show enough motion to be identified as a moving object at all. The geometry of detection adds another layer of mathematical complexity. For us to see an interstellar object, it must pass through a relatively small volume of space, where it's both close enough to the Sun to be illuminated and close enough to Earth to be detected. This creates what we might visualize as a detection bubble around Earth, a region where objects become visible to our instruments. The size of this bubble depends on the size and reflectivity of the object, the sensitivity of our telescopes, and the amount of time we spend looking. For an object like 3I Atlas, this detection bubble might extend out to the orbit of Jupiter or Saturn, still a vast volume of space, but tiny compared to the overall size of our solar system. Objects passing outside this bubble remain forever invisible to us. their presence unknown and unknowable with our current technology. They might pass through the outer reaches of our solar system, influenced by our sun's gravity, even captured into temporary orbits. But if they never enter our detection bubble, we'll never know they were there. The mathematical probability of detection becomes even more intriguing when we consider the three-dimensional nature of space. Interstellar objects can approach our solar system from any direction, not just along the plane where the planets orbit. This means our detection bubble is really a sphere, and objects must pass through this three-dimensional volume to be detected. The probability of any given object passing through this sphere is remarkably small, which makes the detection of objects like 3-Eye Atlas all the more remarkable. Temperature plays a subtle but important role in the mathematics of invisibility. In the cold depths of space, far from any star, interstellar objects cool down to just a few degrees above absolute zero. At these temperatures, they emit almost no thermal radiation, no heat signature that our infrared telescopes could detect. Only when they approach the sun and warm up do they begin to emit detectable amounts of infrared radiation. This thermal invisibility adds another constraint to our ability to detect these objects, particularly those that don't develop the bright cometary tails that make objects like 3-Eye Atlas easier to spot. The development of a comet's tail is itself a mathematical process, governed by the balance between solar heating and the sublimation of volatile ices. As an object like 3-Eye Atlas approaches the sun, its surface temperature rises according to a precise mathematical relationship with distance. When this temperature reaches the sublimation point of various ices, water, carbon dioxide, methane, and others, these materials begin to turn directly from solid to gas, creating the glowing tail that makes the comet visible from Earth. But not all interstellar objects develop these helpful tails. Oumuamua, the first discovered interstellar object, showed no signs of cometary activity despite passing quite close to the Sun. This suggests it had either already lost all its volatile materials during its long journey through interstellar space, or it was composed primarily of rock or metal that wouldn't sublimate even when heated. Such objects remain much harder to detect, visible only through the sunlight they reflect rather than through any light they generate themselves. The mathematics of orbital mechanics determines not just whether we can see an object, but for how long. An interstellar object following a hyperbolic trajectory spends only a limited time within our detection bubble. The faster it's moving, the less time it spends in the region where we can see it. 3-Eye Atlas was visible to our telescopes for several months, but faster moving objects might be detectable for only weeks or even days. This creates a narrow window of opportunity for discovery and study, a brief moment when the mathematics of visibility align in our favor. The challenge of detection is compounded by the fact that we don't know where to look. Unlike asteroids that belong to our solar system, which tend to be concentrated in certain regions like the asteroid belt, interstellar objects can come from any direction. This means we need to survey the entire sky to have any chance of finding them, a task that requires enormous amounts of telescope time and generates vast quantities of data that must be analysed. The data analysis itself involves sophisticated mathematical algorithms that must distinguish real moving objects from the numerous false positives that appear in astronomical images. Cosmic rays hitting the telescope's detector can create spots that look like stars. Satellites passing overhead can leave trails that might be confused with fast-moving asteroids. Even variations in Earth's atmosphere can create artifacts that complicate the search for real objects. The mathematics of signal processing and pattern recognition becomes crucial in separating the wheat from the chaff. Machine learning algorithms are increasingly being employed to tackle this challenge, trained on millions of examples to recognize the subtle signatures of real moving objects. These algorithms apply complex mathematical transformations to the data, looking for patterns that human observers might miss. They can process vast amounts of data far faster than humans, increasing our chances of catching brief appearances of interstellar visitors. But even our best algorithms are limited by the fundamental mathematics of detection. There's a minimum signal-to-noise ratio below which no amount of clever processing can extract a real signal. This creates a hard limit on what we can detect with any given telescope, a mathematical boundary that can only be pushed back by building larger telescopes or developing more sensitive detectors. The future of detecting invisible interstellar objects lies in pushing these mathematical boundaries. New telescopes like the Vera Rubin Observatory will have larger mirrors, gathering more light, and thus able to detect fainter objects. They'll also have wider fields of view, allowing them to survey larger portions of the sky more quickly. The mathematics suggests that these improvements will dramatically increase our detection rate, possibly finding dozens or even hundreds of interstellar objects per year. Space-based telescopes offer another way to improve the mathematics of detection. Above Earth's atmosphere, they can achieve better sensitivity and observe in wavelengths that are blocked by our atmosphere. They can also observe continuously without the interruption of daylight or weather, increasing the probability of catching brief appearances of fast-moving objects. The mathematical advantage of space-based observation could reveal populations of interstellar objects that remain forever invisible from Earth's surface. The mathematics of invisibility also helps us estimate what we're missing. By understanding the detection limits of our instruments and the likely distribution of object sizes and trajectories, astronomers can calculate statistical estimates of the true population of interstellar objects. These calculations suggest that for every 3-eye atlas we detect, there might be millions of smaller objects passing through our solar system unseen. This statistical approach reveals the profound incompleteness of our view of the cosmos. We're like ancient mariners trying to understand the ocean by studying only the largest waves that reach our shore, missing the countless smaller ripples and currents that make up most of the sea's activity. The mathematics tells us that the vast majority of the cosmic activity around us remains invisible, hidden by the fundamental physics of light and distance. The story of 3-eye atlas and our ability to detect it is thus a story of mathematical alignment, of being in the right place at the right time with the right instruments. It passed close enough to the sun to be illuminated, close enough to Earth to be detected, and stayed in our detection zone long enough to be discovered and studied. The mathematics had to work out just right, and they did, giving us this precious glimpse of a visitor from another star system. As we continue to push the boundaries of detection, developing new technologies and new mathematical techniques, we'll undoubtedly discover more of these cosmic visitors. Each discovery will help us refine our mathematical models, improving our estimates of what remains hidden. But the mathematics also tells us that we'll never see everything, that there will always be objects too small, too dark, too distant, or moving too fast for our instruments to detect. This mathematical invisibility is not a flaw in our technology or our understanding. It's a fundamental aspect of our universe. The same laws of physics that allow us to see some objects ensure that others remain forever hidden. It's a humbling reminder that our view of the cosmos, no matter how sophisticated our instruments become, will always be partial, always incomplete. The mathematics of invisibility transforms space from an empty void into a realm full of hidden objects and invisible activity. Every cubic meter of space in our solar system might contain countless tiny particles from other star systems, too small for us to detect individually but collectively, representing a massive flow of material between stars. Every year, objects larger than 3-eye atlas might pass through our solar system, completely undetected, their presence unknown and their secrets unexamined. Yet rather than being discouraging, this mathematical reality is profoundly exciting. It means that space is far richer and more dynamic than we can directly observe. It means that discoveries like 3-eye atlas are just the tip of an enormous cosmic iceberg, visible representatives of a vast invisible population. It means that as our technology improves and our mathematical techniques become more sophisticated, we'll continue to reveal new layers of cosmic activity that were always there but hidden from our view. The universe doesn't hide these objects from us deliberately. They're invisible simply because of the way light works, the vast distances involved, and the limitations of our instruments. The mathematics of invisibility is not a barrier but a challenge, an invitation to develop better tools and cleverer techniques to peer deeper into the cosmic darkness. Every improvement in our detection capabilities reveals new objects, new phenomena, new mysteries to explore. Tonight, as you drift towards sleep, consider the elegant mathematics that governs what we can and cannot see in space. Think about the precise balance of factors that had to align for us to detect 3i Atlas, and the countless similar objects that passed by undetected, because the mathematics didn't quite work out. The universe is performing complex calculations every moment, determining what remains hidden and what briefly emerges into visibility, what stays in shadow and what catches the light. The cosmic game of hide and seek continues all around us, governed by mathematical rules that are both simple in principle and stunning in their implications. Most of the universe remains mathematically invisible to us, hidden not by distance alone, but by the fundamental physics of light and detection. Yet within this mathematical framework, objects like 3i Atlas occasionally emerge from invisibility, brief visitors to the realm of the visible, carrying with them stories from the vast invisible universe that surrounds us. The mathematics tells us they've always been there, passing through our solar system throughout its history, invisible until we develop the mathematical tools and technological eyes to finally see them. And even now, with our best instruments and most sophisticated techniques, we're only seeing the tiniest fraction of what's really there. The few objects large enough and close enough and bright enough to rise above the mathematical threshold of invisibility into the narrow realm of the detectable. The mathematics of cosmic invisibility leads us naturally to wonder about the messages these hidden visitors might be carrying. As we continue our journey through the cosmic night, let's turn our attention to what 3i Atlas and objects like it might be telling us about their home star systems, about the vast journey they've undertaken, and about the gentle exchange of material that connects every star to every other across the galaxy. These silent messengers, drifting through the darkness for millions or billions of years, carry within them whispers from other star systems, encoded not in language but in their very composition, their structure, their chemistry. Every interstellar object is, in essence, a message in a bottle cast into the cosmic ocean by a distant star system. The message isn't written in words or symbols, but in the isotopic ratios of elements, in the mineralogy of rocks, in the chemistry of ices. These physical properties tell the story of where the object formed, under what conditions, and what has happened to it since. When we study an object like 3i Atlas, we're reading a letter from another star, decoding information that no telescope, no matter how powerful, could provide about distant stellar systems. Consider what happens when a star system forms. In the swirling disk of gas and dust around a young star, temperatures and pressures vary dramatically with distance from the center. Close to the star, it's hot enough to vaporize even rock and metal. Farther out, where temperatures drop, water can condense into ice. Even farther still, more volatile substances like methane and carbon monoxide freeze solid. This temperature gradient creates a kind of chemical fingerprint in the objects that form at different distances from the star. By studying the composition of an interstellar visitor, we can determine approximately where in its home system it originally formed. 3 Atlas, with its cometary nature, tells us it likely formed in the outer regions of its home star system, where it was cold enough for water and other volatile substances to condense into ice. The specific mix of ices, the ratio of water to carbon dioxide to methane to more exotic compounds, provides clues about the exact temperature and pressure conditions during its formation. It's like each comet carries a record of the weather in its birthplace, frozen in time and preserved for billions of years. But the whispers from other star systems go deeper than just formation conditions. The isotopic signatures in these objects tell us about the star that created them. Every star has its own nuclear furnace, fusing lighter elements into heavier ones through specific pathways that depend on the star's mass, temperature, and age. These nuclear processes create distinctive patterns in the ratios of different isotopes, atoms of the same element with different numbers of neutrons. When material from a star gets incorporated into planets, asteroids, and comets, it carries these isotopic fingerprints with it. For instance, the ratio of oxygen-16 to oxygen-18, or carbon-12 to carbon-13, can tell us about the type of star that contributed material to an object's formation. Young, massive stars produce different isotopic ratios than older, smaller stars. Stars that formed early in the galaxy's history, when there were fewer heavy elements around, leave different signatures than stars forming today. By analysing these isotopic ratios in interstellar visitors, we're essentially conducting stellar archaeology, learning about stars we've never directly observed and may never be able to study any other way. The journey itself leaves marks on these cosmic messengers. As they travel through interstellar space, they're bombarded by cosmic rays, high-energy particles that zip through the galaxy at nearly the speed of light. These cosmic rays can alter the surface of an object, creating specific chemical changes and even producing rare isotopes through nuclear reactions. The longer an object has been travelling through space, the more cosmic ray damage it accumulates. This damage is like a timestamp, a way of estimating how long ago the object was ejected from its home system. Triae Atlas and other interstellar comets face an additional challenge during their long journey. They slowly lose their most volatile materials. Even in the extreme cold of interstellar space, the lightest molecules can gradually escape, especially from smaller objects with weak gravity. This process, called sublimation, happens incredibly slowly at near absolute zero temperatures, but over millions or billions of years, it can significantly alter an object's composition. The volatiles that remain tell us about the object's size, its journey time, and the conditions it has experienced. The spin of an interstellar object carries information too. Objects ejected from planetary systems often receive a gravitational kick that sets them rotating. This rotation rate can change over time due to various effects, including the emission of gas when the object approaches a star. By measuring how Triae Atlas rotates, scientists can infer details about its ejection from its home system and its subsequent journey. It's like each object carries a gyroscope that records its dynamic history, its tumbles and turns through space. Perhaps most intriguingly, these interstellar messengers might carry organic molecules, the building blocks of life as we know it. Many comets in our own solar system contain complex organic compounds, including amino acids, the components of proteins. If comets from other star systems carry similar materials, they could be spreading the chemical precursors of life throughout the galaxy. Each interstellar visitor might be a seed pod, carrying the potential for life from one star system to another. The discovery of organic molecules on interstellar objects would have profound implications for our understanding of life in the universe. It would suggest that the chemistry that leads to life might be universal, occurring in star systems throughout the galaxy. It would also provide a mechanism for panspermia, the hypothesis that life or its building blocks can spread between star systems. While the journey through interstellar space is harsh, with extreme cold and radiation, some organic molecules and even certain microorganisms might survive, protected in the interior of a large enough object. Triae Atlas, during its passage through our solar system, was too far from Earth for us to directly sample its composition. But we could study the light reflected and emitted from its surface and tail, using spectroscopy to identify some of the molecules present. Each molecule absorbs and emits light at specific wavelengths, creating a spectral fingerprint that we can detect with our telescopes. Through this technique, we can identify water, various ices, dust particles, and sometimes even more complex molecules in the comet's tail. Future missions might be able to do much more, imagine a spacecraft intercepting an interstellar visitor, landing on its surface, and directly analysing its composition. Such a mission would be like opening a time capsule from another star system, reading messages written billions of years ago in the language of chemistry and physics. We could determine not just what elements and molecules are present, but their exact isotopic ratios, their crystal structures, their chemical bonds. We could search for signs of past or present biological activity, for organic molecules that might indicate life existed in the object's home system. The whispers from other star systems aren't just about the past. They also tell us about the present state of our galaxy. The rate at which we detect interstellar objects gives us information about how many are out there, which in turn tells us about the rate at which star systems eject material. This ejection rate is related to the dynamics of planetary system formation and evolution. Young systems, still in the chaotic process of forming planets, likely eject more material than older stable systems. By studying the population of interstellar objects, we're learning about the life cycles of planetary systems throughout the galaxy. The directions from which interstellar objects arrive also carry information. If objects came from random directions uniformly, it would suggest a very old population that has had time to mix throughout the galaxy. But if they show preferred directions, it might indicate recent events like the dissolution of a star cluster or the passage of our solar system through a region of enhanced stellar density. 3 Atlas came from a particular direction in the constellation Lyra, and as we detect more objects, we'll build up a map of the cosmic currents that carry these messengers through space. The velocities of interstellar objects relative to our solar system tell another part of the story. Objects moving very fast relative to us might come from distant parts of the galaxy, with different orbital velocities around the galactic center. Slower objects might come from nearby stars that share similar orbits to our Sun. The velocity distribution of interstellar visitors is like a survey of our galactic neighborhood, telling us about the motions and distributions of stars we might never directly observe. Some interstellar objects might carry even more dramatic messages. If a star exploded as a supernova, it would eject material at enormous velocities, some of which might eventually pass through our solar system. These objects would carry distinctive isotopic signatures of nuclear processes that only occur in supernova explosions. They might be enriched in rare elements that can only be produced in such extreme events. Finding and studying such an object would be like receiving a direct sample from one of the most violent and creative events in the universe. Similarly, objects ejected from systems with exotic stars, white dwarfs, neutron stars, or even black holes, would carry unique signatures. A comet that once orbited a white dwarf might have a surface altered by intense ultraviolet radiation. Material ejected from the vicinity of a neutron star might show effects of enormous magnetic fields. These exotic messengers would tell us about environments we can barely imagine, conditions so extreme that they push the boundaries of physics. The chemistry of interstellar visitors might also reveal the presence of multiple stars in their home systems. Many stars exist in binary or multiple star systems, and the complex gravitational dynamics of such systems are particularly effective at ejecting objects into interstellar space. The heating patterns, the distribution of volatiles, and the orbital characteristics of ejected objects would all be influenced by the presence of multiple stars. By studying these properties, we could learn about the architecture of distant star systems. There's also the tantalizing possibility that some interstellar objects might carry technological signatures. While this remains highly speculative, it's worth considering that advanced civilizations, if they exist, might deliberately or accidentally release objects into interstellar space. These could be probes designed to study other star systems, defunct satellites or spacecraft ejected from their home systems, or even deliberate attempts at interstellar communication. While 3I Atlas shows no signs of artificial origin, the possibility adds another dimension to our study of interstellar visitors. The whispers from other star systems carried by objects like 3I Atlas are teaching us that the galaxy is more interconnected than we ever imagined. Material flows between star systems not randomly, but through specific pathways determined by stellar motions and gravitational dynamics. This flow has been happening since the galaxy formed, creating a vast network of material exchange that connects every star system to every other. We're not isolated islands in space, but part of a galactic community where information, encoded in physical material, constantly flows between members. Each interstellar visitor we detect adds another voice to this cosmic conversation. Some whisper about young star systems still in formation, others about ancient stars that died billions of years ago. Some carry messages about peaceful, stable planetary systems like our own, others about chaotic systems where planets migrate and collide. Together, these whispers are helping us understand the diversity of star systems in our galaxy, the processes that shape them, and our own place in this vast cosmic ecosystem. The study of these cosmic messengers is also changing how we think about our own solar system. We now know that our Sun has likely ejected countless objects into interstellar space over its history. These objects, carrying information about our solar system, are even now journeying to distant stars. Perhaps billions of years from now, one of them will pass through an alien solar system where it might be detected and studied by whatever intelligence has evolved there. They'll analyze it just as we analyze 3i Atlas, trying to understand what it tells them about its home system. This reciprocal exchange creates a kind of cosmic library, where information about star systems is encoded in physical objects that travel between them. It's a library without walls, where the books themselves journey between readers, carrying their stories across impossible distances and incomprehensible spans of time. 3i Atlas is just one book from this vast library, briefly available for us to read before it continues its journey to other readers around other stars. The whispers from other star systems also remind us of the deep timescales involved in cosmic processes. The material that makes up 3 Atlas might have been part of several different star systems over the history of the galaxy. Atoms forged in one star might have been incorporated into planets around another star, then ejected as part of a comet that travelled to a third star system. This recycling of material connects not just different places in the galaxy, but different times in its history. As we develop more sophisticated techniques for studying interstellar visitors, we'll be able to read these whispers more clearly. New telescopes will allow us to detect fainter objects and study them in greater detail. Advanced spectrographs will identify more complex molecules and more subtle isotopic signatures. And perhaps one day, sample return missions will bring pieces of interstellar visitors back to Earth for detailed laboratory analysis. The whispers from other star systems carried by objects like 3i Atlas are gradually helping us understand our place in the cosmic order. We're learning that star systems are not isolated, but connected through a vast network of material exchange. We're discovering that the processes that shaped our solar system are universal, occurring throughout the galaxy. And we're beginning to appreciate that the story of any single star system, including our own, can only be fully understood in the context of its connections to other systems. These cosmic messengers remind us that we're part of something much larger than our single star and its planets. We're participants in a galactic ecosystem where material, energy, and perhaps even life flow between star systems over billions of years. The whispers from other star systems carried by interstellar visitors like 3i Atlas are telling us that we're not alone, not isolated, but part of a vast cosmic community that has been exchanging messages since the galaxy began. Now, as we delve even deeper into the mysteries revealed by these cosmic wanderers, let's consider how empty space itself becomes a kind of archaeological site filled with invisible artifacts from across the galaxy. The void between stars, which seems so empty and barren, is actually rich with history, packed with objects that carry records of cosmic events stretching back billions of years. Each passing object, whether we can see it or not, is like an artifact in a vast museum without walls, a museum where the exhibits float freely through the darkness, occasionally passing close enough for us to examine them. When archaeologists on Earth excavate ancient sites, they carefully sift through layers of soil and sediment, each layer representing a different period in history. The deeper they dig, the further back in time they travel. Space archaeology works differently but follows similar principles. Instead of digging down through layers, we're observing objects that have been traveling through space for different amounts of time, each one preserving information about the era when it was ejected from its home system. The cosmos around us is stratified not in physical layers, but in temporal ones, with objects from different cosmic epochs mixing together in the space around us. 3. Atlas, in this context, is like a pottery shard or a stone tool found at an archaeological site. Just as archaeologists can determine when and where an artifact was made by analysing its composition and style, astronomers can deduce when and where 3I Atlas formed by studying its physical and chemical properties. The object itself is the artifact, carrying information about a place and time we cannot directly observe. It's a tangible piece of another star system's history, delivered to our doorstep by the patient currents of interstellar space. The archaeological richness of empty space becomes even more apparent when we consider the sheer number of objects that must be present. If our current estimates are correct, there could be trillions of interstellar objects within our solar system at any given moment, ranging from microscopic dust grains to mountain-sized chunks of rock and ice. Each one is an artifact from another star system, a piece of evidence about conditions elsewhere in the galaxy. Together they form a vast collection that would make any museum curator envious, if only we could see and study them all. But unlike artifacts in a traditional museum, these cosmic relics aren't organized or catalogued. They're scattered randomly through space, mixing objects from different sources and different times. An object ejected from a nearby star 10 million years ago might pass right by one that's been traveling for billions of years from the other side of the galaxy. Young and old, near and far, all jumbled together in the vast archaeological site that is interstellar space. This mixing makes the archaeology more challenging but also more interesting, as each new discovery could come from anywhere and any time in the galaxy's history. The preservation conditions in space are extraordinary from an archaeological perspective. The extreme cold and vacuum of interstellar space act like a perfect preservation environment, keeping objects essentially unchanged for billions of years. Unlike artifacts on Earth, which decay and degrade over time, objects in space remain frozen in time, their properties locked in place from the moment they were ejected from their home systems. When we study 3I Atlas, we're seeing it almost exactly as it was when it left its parent star, minus only the subtle effects of cosmic ray bombardment and slow volatile loss. This exceptional preservation means that interstellar objects can carry incredibly detailed information about their origins. The crystal structure of minerals, the ratios of different molecules, even the arrangement of atoms and complex organic compounds, all of these can survive the journey through interstellar space. It's as if each object is a perfectly preserved time capsule, waiting to be opened and studied. The information density in these cosmic artifacts is remarkable, with each one potentially telling us about stellar nucleosynthesis, planetary formation, chemical evolution, and possibly even biological processes in its home system. The temporal distribution of these cosmic artifacts tells its own story. Objects ejected recently from nearby stars are like contemporary artifacts, showing us what's happening in our galactic neighborhood right now. Objects that have been traveling for millions of years are like artifacts from the classical period, representing conditions in the galaxy when our ancestors were just beginning to evolve, and objects that have been journeying for billions of years are like prehistoric artifacts, carrying information from the early days of the galaxy, when the first generations of stars were still young. Some of these ancient travelers might predate our solar system entirely. They could carry material from stars that died before our sun was born, preserving samples of the galaxy's early chemistry. These objects would be like finding artifacts from a civilization that predated all known history, offering glimpses into eras we can only theorize about. The isotopic signatures in such objects could tell us about the galaxy's chemical evolution, how the abundance of different elements has changed over cosmic time. The concept of space as an archaeological site extends beyond individual objects to patterns and distributions. Just as archaeologists look for patterns in artifact distributions to understand ancient trade routes and cultural exchanges, astronomers can look for patterns in the origins and trajectories of interstellar objects. Are there preferred directions from which objects arrive? Do objects from certain directions have different compositions? These patterns could reveal ancient stellar encounters, dissolved star clusters, or streams of material from long-dead stars. The archaeological interpretation of space also includes the search for rare and unusual artifacts. Most interstellar objects are probably fairly ordinary comets and asteroids, the cosmic equivalent of common pottery shards. But occasionally, we might encounter something unusual, an object with a bizarre composition, an unexpected structure, or properties that challenge our understanding of planetary formation. These rare finds, like Oumuamua with its unusual elongated shape, are the equivalent of finding a golden mask or a perfectly preserved manuscript, objects that can revolutionize our understanding of the past. The layering of history and space is complex and three-dimensional. Unlike terrestrial archaeological sites where older layers are generally below younger ones, in space, objects from different eras intermingle freely. An object that formed 10 billion years ago might pass right by one that formed yesterday. This mixing means that every observation potentially samples a different era of galactic history. It's like having an archaeological site where artifacts from all periods of history are scattered randomly across the surface, requiring careful analysis to determine which era each one represents. The archaeological value of interstellar objects extends to understanding catastrophic events in galactic history. Supernovae, stellar collisions, and planetary system disruptions all leave their marks on the objects they eject. Finding and studying objects from such events would be like discovering artifacts from Pompeii or other disaster sites, preserving moments of dramatic change in stellar systems. The chemistry and structure of these objects could tell us about events we can't observe directly, expanding our understanding of stellar evolution and death. Empty space also preserves evidence of gentler processes, the slow evolution of planetary systems, the gradual migration of planets, the patient accumulation of material into larger bodies. All of these processes influence what gets ejected into interstellar space and when. By studying the population of interstellar objects, we're essentially conducting a demographic survey of planetary system evolution, learning about the typical life cycles of systems like our own. The archaeological perspective transforms our view of Three-Eye Atlas from a simple cosmic visitor to a valuable historical artifact. Every measurement we make, every spectrum we collect, is like carefully documenting an archaeological find. We're recording not just the object's current properties, but what those properties tell us about its history, its origins, and the conditions that created it. Future astronomers will look back at our observations of Three-Eye Atlas the way we look at early archaeological excavations, as the beginning of our understanding of the cosmic archaeological record. The tools we use to study these cosmic artifacts are becoming increasingly sophisticated, like the evolution of archaeological techniques from simple digging to ground-penetrating radar and chemical analysis. Modern spectroscopy allows us to identify molecules from afar, like being able to determine the composition of an ancient artifact without touching it. Orbital analysis lets us trace back an object's path through space, like reconstructing ancient trade routes from the distribution of artifacts. And future sample return missions will be like bringing artifacts back to the laboratory for detailed study. The archaeological richness of space raises profound questions about what we're missing. For every Three-Eye Atlas we detect, there might be millions of smaller or darker objects passing by unnoticed. It's like having access to only the largest and most obvious artifacts at an archaeological site, while knowing that countless smaller but potentially equally important items remain buried. The true archaeological record of space is vastly richer than what we can currently observe, hidden by the limitations of our technology and the fundamental physics of detection. This hidden archaeological record might contain extraordinary treasures. Perhaps there are objects carrying clear signs of biological processes from other worlds. Perhaps there are artifacts from exotic stellar environments we've never observed. Perhaps there are even objects of artificial origin, technological artifacts from civilizations that rose and fell long before Earth formed. While we have no evidence for such extraordinary finds yet, the archaeological perspective reminds us that absence of evidence is not evidence of absence, especially when we can only examine such a tiny fraction of what's actually there. The concept of space archaeology also highlights the importance of preservation and documentation. Every interstellar object we detect is a unique artifact that will never return. Once 3i Atlas leaves our solar system, it's gone forever, taking its secrets with it. This creates an urgency to observe and document these objects as thoroughly as possible while we can. We're like archaeologists at a site that's about to be destroyed, racing to record as much information as possible before it's lost forever. The archaeological interpretation extends to our own solar system's contribution to the cosmic record. We're not just discovering artifacts, we're also creating them. Every comet or asteroid ejected from our solar system becomes an artifact carrying information about our sun and planets. These objects join the vast archaeological record of space, where they might one day be discovered and studied by alien astronomers trying to understand our corner of the galaxy. We're simultaneously archaeologists studying the cosmic past and artifact creators, contributing to the cosmic future. The temporal depth of the cosmic archaeological record is staggering. On Earth, archaeology typically deals with timescales of thousands or occasionally millions of years. In space, we're dealing with billions of years, spanning significant fractions of the universe's entire history. Objects like 3i Atlas might have been travelling since before Earth had an oxygen atmosphere, before complex life evolved, before our solar system had even finished forming. They're artifacts from deep time, carrying messages from eras so remote that they challenge our ability to comprehend. The archaeological perspective also emphasizes the interconnectedness of cosmic history. Just as terrestrial archaeology reveals trade networks and cultural exchanges between ancient civilizations, space archaeology reveals the material exchanges between star systems. Every interstellar object is evidence of these connections, proof that star systems don't evolve in isolation, but influence each other through the objects they exchange. The galaxy emerges not as a collection of separate stellar islands, but as a connected network with a shared material history. As we continue to develop our ability to detect and study interstellar objects, we're essentially becoming better cosmic archaeologists. New telescopes are like new excavation tools, allowing us to find smaller and fainter artifacts. Improved spectroscopic techniques are like better chemical analysis methods, revealing more details about composition and origin. And growing databases of discoveries are like expanding archaeological collections, allowing us to see patterns and connections we couldn't see from individual finds. The archaeology of empty space is teaching us that the void between stars is anything but empty. It's filled with history, packed with artifacts from across the galaxy and throughout cosmic time. Each object tells a story, carries information, preserves a moment from somewhere and someone else. 3i Atlas is just one artifact from this vast collection, but studying it has opened our eyes to the archaeological richness that surrounds us. Space itself is a museum, an archive, an archaeological site of unimaginable scope and depth. This archaeological perspective transforms our understanding of what it means to explore space. We're not just looking for new worlds or searching for life. We're excavating the history of the galaxy, one cosmic artifact at a time. Every interstellar visitor we detect adds another piece to the vast puzzle of galactic evolution. And somewhere in this cosmic archaeological record might be the evidence that answers our deepest questions about our origins, our uniqueness, and our future in the cosmos. The notion of space as an archaeological treasure trove leads us naturally to contemplate the profound ways in which time and distance interweave in the journeys of these cosmic wanderers. As we settle even deeper into our cosmic contemplation, let's explore how objects like 3i Atlas exist in a realm where time itself becomes a form of distance, where millions of years translate into light years of travel, and where the past, present, and future of different star systems overlap and intermingle in ways that challenge our earthbound understanding of temporality. When we observe 3i Atlas passing through our solar system, we're witnessing a moment that connects vastly different epochs of cosmic history. This object might have begun its journey when Earth's most complex life forms were single-celled organisms floating in primordial seas. During its travels through interstellar space, our planet underwent extraordinary transformations. Continents formed and split apart, life exploded into countless forms, mass extinctions came and went, and eventually a species evolved capable of detecting this ancient traveller. Yet for 3i Atlas itself, drifting through the cold darkness between stars, time passed differently, almost imperceptibly, in a state of near-perfect preservation. This temporal paradox is fundamental to understanding interstellar objects. They exist in what we might call deep time, a temporal realm where millions of years are just brief moments in journeys that span billions of years. While civilizations rise and fall on planets, while entire species evolve and go extinct, these objects continue their patient trajectories through space, unchanged and unchanging, carrying their ancient messages across the galaxy. They are temporal bridges, connecting epochs that would otherwise be completely separated by the vast gulf of time. The relationship between time and distance for these objects follows Einstein's insights about space-time, but in ways that stretch our intuition. For 3i Atlas, travelling at perhaps 30 kilometers per second relative to the stars it passes, time flows normally from its perspective. But the distances it must cover are so vast that even at these tremendous speeds, millions of years pass between stellar encounters. If we could somehow ride along with 3i Atlas, we would experience time normally, watching the slow drift of stars across the sky as centuries passed like days, millennia like months, and millions of years like decades. Consider the mathematics of these temporal journeys. A light year, the distance light travels in 1 year, is about 9.5 trillion kilometers. An object like 3i Atlas, moving at a more modest 30 kilometers per second, would take about 10,000 years to travel a single light year. The nearest star to our Sun is about 4.2 light years away, meaning even a relatively fast interstellar object would need 40,000 years to make the journey. And most interstellar journeys are much longer, spanning dozens or hundreds of light years, requiring millions of years to complete. During these vast temporal odysseys, the galaxy itself evolves around these travelling objects. Stars are born and die, spiral arms rotate and reform, stellar clusters dissolve, and new ones form. An object ejected from a star cluster that no longer exists might pass through our solar system, carrying information about stellar groupings that dissolved millions of years ago. It's like receiving a letter from a city that has long since crumbled to dust, written in a language of chemistry and physics that we're only now learning to read. The temporal layers embedded in objects like 3i Atlas are remarkably complex. First, there's the age of the material itself, the atoms forged in stellar furnaces perhaps billions of years ago. Then there's the age of the object's formation, when those atoms assembled into the comet or asteroid we now observe. Next comes the duration of its residence in its home system, which might have lasted millions or billions of years. Finally, there's the journey time through interstellar space, another span of millions or billions of years. Each of these temporal layers leaves its mark on the object, creating a kind of temporal stratigraphy that we can decode through careful analysis. The concept of simultaneity becomes strange when considering interstellar objects. 3I Atlas might have been ejected from its home system at the same time, in cosmic terms, that our solar system was forming. But same time loses its meaning across such vast distances. Due to the finite speed of light, we can't even see its home star as it is now, but only as it was years, decades, or centuries ago. The object itself has travelled slower than light, taking millions of times longer to reach us than light from its home star. In a sense, 3I Atlas exists in a temporal bubble, disconnected from both its origin and its destination, suspended in a travelling present that connects two different cosmic epochs. This temporal suspension has profound implications for what these objects can tell us. They're not just samples from other places, but from other times. An object that left its home system 1 billion years ago carries information about conditions in the galaxy when it was significantly younger, when the chemical composition was different, when stellar populations were different, when the rate of star formation was different. By studying objects of different ages and origins, we're essentially conducting temporal astronomy, observing the galaxy not just as it is, but as it was across vast spans of time. The preservation of information across these temporal gulfs is remarkable. In the cold of interstellar space, chemical reactions essentially stop. Radioactive decay continues, providing a kind of clock that can tell us how long an object has been travelling, but most other processes freeze. This means that when we study 3I Atlas, we're seeing it almost exactly as it was when it left its home system, a pristine sample from another time and place. It's as if time stopped for the object during its interstellar journey, creating a perfect time capsule that we can now open and examine. The intersection of different temporal scales becomes even more interesting when we consider the future. 3I Atlas will leave our solar system and continue its journey for perhaps billions more years. Long after our sun has died and our solar system has dispersed, this object will still be travelling through space, carrying information about our brief encounter with it. It might pass through other star systems where future civilizations could detect and study it, learning about our corner of the galaxy in our era. In this way, interstellar objects become temporal messengers, carrying information not just through space but through time, connecting different epochs of galactic history. The concept of time dilation, while minimal at the speeds interstellar objects travel, still plays a subtle role. According to special relativity, time passes slightly slower for moving objects. While this effect is tiny for objects moving at typical interstellar velocities, perhaps a few parts in 1 billion, over millions of years, it adds up. An object that has been travelling for 1 billion years might have aged a few years less than the galaxy around it. It's a small effect, but it means these objects are literally younger than they should be, having experienced less time than stationary objects of the same age. The temporal aspects of interstellar objects also relate to the concept of cosmic archaeology we explored earlier, but now we see that we're not just digging through space but through time itself. Each object we detect is a temporal artifact, a piece of the past delivered to our present. The distribution of ages among interstellar objects tells us about the history of stellar ejection, about when and how star systems lose material to interstellar space. Young objects tell us about recent events, while ancient objects tell us about the deep history of our galaxy. The way time and distance interweave for these objects creates interesting paradoxes. An object ejected from a nearby star 1 million years ago might arrive at the same time as one ejected from a distant star 10 million years ago. Objects from the same star but ejected at different times might arrive centuries or millennia apart. This temporal scrambling means that the objects passing through our solar system at any given moment represent a random sampling of different times and places throughout the galaxy's history. The future detection of interstellar objects will allow us to build up a temporal map of our galaxy. By determining the ages and origins of many objects, we can reconstruct the history of stellar ejection, the evolution of planetary systems, and the changing conditions in different regions of the galaxy over time. It's like having a time machine that brings samples from different eras to our present, allowing us to study the galaxy's evolution directly, rather than just inferring it from observations of distant stars. The temporal journey of 3i Atlas also connects to fundamental questions about causality and influence in the galaxy. Events in distant star systems millions of years ago, the formation of planets, the migration of giant worlds, stellar encounters, led to the ejection of this object. Those ancient events are now having consequences in our solar system as we observe and study their messenger. In this way, the past of distant places becomes part of our present, and our present observations will become part of the future understanding of the galaxy. The deep time perspective of interstellar objects also relates to the search for life in the universe. If life exists elsewhere, the exchange of material between star systems means that evidence of it might be preserved in interstellar objects. But the temporal aspects add complexity. Life that existed millions or billions of years ago in a now dead system might have left traces in objects currently passing through our solar system. We might discover evidence of alien life that went extinct before Earth even formed, raising profound questions about the persistence and prevalence of life in the cosmos. The temporal dimensions of objects like 3i Atlas remind us that the universe operates on timescales that dwarf human experience. Our entire recorded history is just a blink compared to the journeys of these objects. Civilizations could rise and fall dozens of times during a single interstellar journey. This perspective is both humbling and inspiring. Humbling because it shows how brief our existence is in cosmic terms, but inspiring because it connects us to the vast temporal tapestry of the galaxy. As we observe more interstellar objects, we'll begin to see patterns in their temporal distributions. Are older objects more common than younger ones? Do objects of different ages have different compositions, reflecting the chemical evolution of the galaxy? Are there temporal clusters that might indicate specific events in galactic history that ejected large numbers of objects? These temporal patterns will help us understand not just the current state of our galaxy, but its entire evolutionary history. The way time becomes distance for interstellar objects also has practical implications for future space exploration. If we ever develop the technology to catch up with and study these objects, we'll need to account for their temporal journeys. An object that passed through our solar system might be studied centuries later and millions of kilometers away, but it will still carry the same temporal information, the same connection to its ancient origins. In a sense, chasing interstellar objects would be like chasing the past itself, trying to catch up with messages sent millions of years ago. The temporal aspects of 3i Atlas and its kin transform our understanding of the galaxy from a collection of stars existing in a shared present to a temporal web where past, present and future are intricately connected. Objects ejected from stars in the past arrive in our present and continue into the future. Our present ejections will become future arrivals at distant stars. This temporal circulation creates a kind of galactic memory, where information about different times and places is constantly in motion, creating connections across both space and time. The deep time perspective also raises philosophical questions about the nature of existence and persistence. 3 Atlas has existed for perhaps billions of years, far longer than any mountain on Earth, longer than our species, longer than complex life on our planet. In what sense does an object that has been travelling unchanged through space for such vast spans of time exist in the way we normally think about existence? It seems to exist outside of normal time, in a realm where millions of years pass without significant change, where the object itself becomes a kind of temporal constant in an ever-changing galaxy. As we continue to contemplate these temporal dimensions, we begin to see that interstellar objects like 3i Atlas are more than just space rocks or ice balls. They're temporal ambassadors, representatives of other times as much as other places. They carry with them the deep history of our galaxy, connecting us to cosmic epochs we could never otherwise access. Through them we can touch the past, understand the present, and perhaps glimpse the future of our cosmic neighborhood. The interweaving of time and distance in the journeys of these objects reveals the galaxy to be not just a structure in space, but a process in time. Stars form and die, planets emerge and evolve, and all the while, countless objects journey between them, carrying information across the vast temporal gulf. 3i Atlas is just one thread in this temporal tapestry, but by studying it, we're learning to see the entire pattern, a pattern that extends from the galaxy's birth to its far future, with our brief moment of observation just one small but meaningful point in the vast temporal flow. The cosmos continues its patient circulation whether we observe it or not, and as we reach the final contemplation of our journey tonight, let's return to where we began, but with eyes now open to the vast invisible population surrounding us. The question, was 3 Atlas always invisible until now, has taken us through realms of cosmic wonder, from the mathematics of invisibility to the whispers between stars, from gentle giants we cannot see to the profound silence of cosmic distances. Now, as we prepare for the deepest rest, let's weave together all these threads into a final understanding of what it means to live in a universe where most of what exists remains forever hidden from our view, yet where every invisible thread connects us to the vast tapestry of cosmic existence. The journey we've taken tonight has revealed that 3i Atlas is not an anomaly, but a representative, not an exception, but an example of the constant flow of cosmic traffic through our solar system. For every moment of human history, for every breath our ancestors took, for every sunrise and sunset that has ever occurred on Earth, objects like 3i Atlas have been passing through our cosmic neighborhood, invisible and unknown. They were there when the pyramids were built, sailing silently through the outer reaches of our solar system. They were there when life first emerged from Earth's primordial oceans, carrying their ancient cargo through the darkness. They were there when our solar system itself was forming, perhaps contributing material to the very planets we now call home. This perpetual invisibility speaks to something profound about the nature of reality itself. We live in a universe where most of what exists cannot be seen, where the visible is the exception rather than the rule. Dark matter outweighs visible matter by a factor of 5. Dark energy comprises even more of the universe's content, and now we know that even ordinary matter, the stuff we thought we understood, is mostly invisible to us when it takes the form of interstellar wanderers passing through the darkness. The discovery of 3i Atlas hasn't just added one more object to our catalogue of cosmic phenomena, it has fundamentally changed our understanding of how full the emptiness around us really is. Consider what this means for our perception of our cosmic environment. Every cubic astronomical unit of space in our solar system might contain thousands of interstellar dust grains, hundreds of pebble-sized objects, dozens of boulder-sized rocks, and occasionally mountain-sized or even larger bodies, all invisible to our most powerful telescopes. We're not living in a sparse cosmic suburb, but in a bustling cosmic city, where most of the inhabitants are invisible to us. The space between planets, which looks empty to our eyes and even to most of our instruments, is actually thick with cosmic wanderers, each one carrying stories from distant stars, each one a thread in the vast web of galactic connection. The invisibility of these objects until now also speaks to the evolution of human consciousness and capability. For all of human history until the last few decades, we lack the technological eyes to see these cosmic visitors. But more than that, we lack the conceptual framework to even imagine them. The idea that objects could travel between star systems, that material could be exchanged across the galaxy, that our solar system could be regularly visited by cosmic wanderers from distant suns. These concepts required not just better telescopes, but a fundamental shift in how we understand our place in the universe. The visibility of 3i Atlas is thus not just a technological achievement, but a consciousness achievement, an expansion of human awareness to encompass previously unimaginable possibilities. The cosmic perspective we've gained tonight transforms the darkness around us from an empty void into a rich, dynamic environment full of invisible activity. Every direction we look, objects are moving through space, following trajectories that might bring them into brief visibility or might keep them forever hidden. Some are approaching our solar system right now, still years or decades from their closest approach. Others are leaving, having passed through without our knowledge, carrying their secrets back into the interstellar darkness. Still others are passing through the outer reaches of our solar system, too distant and dark for us to detect, their presence known only to the universe itself. This invisible population represents a kind of cosmic democracy, where objects of all sizes and compositions from all origins and ages share the same space. A grain of dust from a star that died billions of years ago might pass right by a boulder ejected from a young star system just millions of years ago. Ancient and young, large and small, rocky and icy, all intermingle in the darkness, creating a cosmic mixture that defies easy categorization. The invisible population around us is not uniform but magnificently diverse, representing the full range of cosmic history and stellar evolution. The fact that these objects have always been invisible until now raises profound questions about what else might be hidden from our current perception. If we've only just discovered that our solar system is constantly visited by interstellar objects, what other cosmic phenomena remain invisible to us? Perhaps there are entirely different categories of cosmic wanderers that we haven't yet imagined. Perhaps there are forms of matter or energy that pass through our solar system regularly, but interact so weakly with ordinary matter that we have no way to detect them. Perhaps the universe is full of invisible structures and processes that we won't discover until we develop new ways of looking, new ways of thinking, new ways of being conscious of cosmic reality. The story of 3i Atlas also reminds us that invisibility is not permanent. What was invisible yesterday might become visible tomorrow as our technology improves. What seems beyond detection today might be routine observation in the future. The boundary between the visible and invisible is not fixed, but constantly shifting as we develop better instruments and deeper understanding. Every improvement in our telescopes, every advance in our detection methods, every refinement in our analysis techniques pushes back the veil of invisibility a little further, revealing new layers of cosmic activity that were always there but hidden from our view. The contemplation of cosmic invisibility also brings us face to face with the limits of human perception and the vastness of what we don't know. We're like children who have just learned to open their eyes, seeing for the first time a room that was always around us but previously invisible. And just as a child's world expands as they develop new ways of perceiving and understanding, our cosmic world is expanding as we develop new ways of detecting and interpreting the universe around us. The discovery of interstellar objects is part of humanity's growing up, our gradual awakening to the true nature of the cosmos we inhabit. The invisible nature of most interstellar objects also protects us from a kind of cosmic overwhelm. If we could see every object passing through our solar system, the sky might appear so full of moving points that we could hardly make sense of it. The invisibility acts as a kind of filter, allowing us to perceive the cosmos at a rate we can process and understand. We see just enough to know that there's vastly more we're not seeing, just enough to inspire wonder without inducing paralysis. The universe reveals itself to us gradually, at a pace matched to our ability to comprehend. As we've explored tonight, the invisibility of objects like 3i Atlas is not just about physical detection, but about temporal perception. These objects exist in deep time, their journeys spanning epochs that dwarf human experience. An object that takes 1,000,000 years to cross between stars exists in a temporal realm that we can understand intellectually but not experientially. Its invisibility is not just about being too dark to see, but about operating on timescales too vast for us to truly grasp. We're temporal mayflies trying to perceive processes that unfold over geological and astronomical timescales. The cosmic invisibility we've been contemplating also extends to the connections between things. The gravitational threads that connect every object to every other, the exchanges of material between star systems, the patterns of cosmic circulation. These are all invisible to direct perception but real in their effects. 3 Atlas is connected to every star it has passed, every object it has encountered, every gravitational field it has traversed. These connections are invisible, but they shape its trajectory, its rotation, perhaps even its composition. We live in a universe where the invisible connections might be more important than the visible objects, where the relationships between things matter as much as the things themselves. The discovery that our solar system has always been visited by invisible interstellar objects also changes our understanding of Earth's history. Every major event in our planet's past, the formation of the moon, the emergence of life, the extinction of the dinosaurs, the rise of humanity, happened while invisible cosmic wanderers were passing through our solar system. Some of these objects might have influenced these events in ways we don't yet understand. Perhaps an invisible interstellar object gravitationally perturbed an asteroid that then impacted Earth. Perhaps cosmic dust from interstellar visitors contributed essential molecules to Earth's early chemistry. The invisible population has always been part of our story, even when we didn't know it existed. Looking forward, the knowledge that we're surrounded by invisible cosmic wanderers opens up extraordinary possibilities for future exploration and discovery. As our detection capabilities improve, we'll undoubtedly discover more and more of these objects. Each discovery will be like turning on a new light in a dark room, revealing another corner of the cosmic environment we inhabit. Future generations might look back at our time as the moment when humanity first became aware of the invisible population, the beginning of our true understanding of our cosmic neighborhood. The invisible objects passing through our solar system right now might include some of the most interesting and valuable objects in the universe. Perhaps there's an object carrying clear evidence of life from another star system, too dark and distant for our current telescopes to detect. Perhaps there's a chunk of material from a type of star we've never observed, carrying information about exotic stellar processes. Perhaps there's even an artificial object, a probe or artifact from another civilization, disguised as a natural object or simply too small and dark for us to notice. The invisible population might contain treasures beyond our imagination, waiting to be discovered. The contemplation of cosmic invisibility also teaches us about the nature of scientific progress. Every generation of scientists thinks they finally understand what's out there, only to discover that they were seeing just a small fraction of reality. The discovery of interstellar objects is humbling in this regard, reminding us that even in our own solar system, even in our cosmic backyard, most of what's there remains invisible to us. It's a reminder to approach the universe with humility, always ready to be surprised, always open to discovering that reality is richer and stranger than we imagined. The invisible cosmic population also represents a kind of cosmic commons, a shared resource that belongs to no single star system but to the galaxy as a whole. These objects carry material and information between stars, creating a slow but steady exchange that enriches every system they pass through. They're like a cosmic library where the books themselves travel between readers, where information is preserved not in static archives, but in eternal motion. The invisible population is thus not just a collection of objects, but a dynamic information system, a way for the galaxy to share knowledge across vast distances and times. As we near the end of our contemplation, it's worth reflecting on how the story of 3i Atlas and the invisible population it represents has changed our emotional relationship with the cosmos. The universe might seem less empty now, less cold, less indifferent. Knowing that we're surrounded by invisible cosmic wanderers, each carrying stories from distant stars, makes space feel less like a void and more like an ocean full of messages in bottles, most of them invisible, but all of them real. We're not alone in an empty universe, but surrounded by countless cosmic companions, even if we can't see them. The invisibility of most interstellar objects also adds a layer of mystery and wonder to our existence. Every night when we look up at the stars, we can know that between us and those distant lights, thousands of invisible objects are passing, each one a cosmic secret, each one a story we might never read. This hidden population adds depth to the night sky, transforming it from a two-dimensional backdrop of stars into a three-dimensional space full of invisible activity. The darkness between stars is not empty but full, not static but dynamic, not known but mysterious. The philosophical implications of cosmic invisibility extend to questions about the nature of existence itself. Do things that we can never detect, that have no measurable effect on us, really exist in any meaningful sense? The invisible interstellar objects passing through our solar system suggest that yes, existence is not dependent on observation, that the universe is full of real things that we might never perceive. This invisible reality is as real as the visible one, perhaps more real because it represents the vast majority of what's actually there. The story of Three-Eye Atlas has also shown us that the boundary between visible and invisible is permeable. Objects drift in and out of visibility depending on their distance, their composition, their activity, and our ability to detect them. Through Atlas itself emerged from invisibility as it approached our Sun, became visible for a brief time, and has now returned to invisibility as it heads back into interstellar space. This cycle of visibility and invisibility is not unique to Three-Eye Atlas, but is the normal pattern for interstellar objects. They spend most of their existence invisible, with only brief moments of visibility when conditions are just right. The invisible population of interstellar objects also represents a kind of cosmic memory, preserving information about star systems that might no longer exist. Some of the objects passing invisibly through our solar system right now might come from stars that died billions of years ago, from planetary systems that were destroyed in cosmic catastrophes, from regions of the galaxy that have been completely transformed since these objects began their journeys. They're like invisible time capsules, carrying memories of cosmic events that no one witnessed, preserving information about places and times that would otherwise be completely lost. As we prepare to conclude our journey tonight, consider how the revelation of the invisible population around us might influence humanity's future. Knowing that we're surrounded by cosmic wanderers might inspire new technologies designed to detect and study them. It might motivate missions to intercept and sample them. It might even influence our philosophy and spirituality, our sense of our place in the universe. The discovery that Three-Eye Atlas was always invisible until now is not just a scientific finding, but a transformation in human consciousness, an expansion of our awareness to encompass previously hidden realms of reality. The invisible cosmic population also raises questions about our own contributions to this galactic exchange. Our solar system has been ejecting objects into interstellar space for billions of years, and we continue to do so today. These objects join the invisible population, becoming cosmic wanderers that might one day pass through other star systems. Some of them might carry evidence of Earth biology, traces of our atmosphere, perhaps even artifacts of human civilization if we ever launch interstellar probes. We're not just discovering the invisible population, we're contributing to it, adding our own invisible messengers to the cosmic flow. The contemplation of cosmic invisibility ultimately brings us to a profound realization. We live in a universe where most of reality is hidden from us, where the visible is just a tiny fraction of what exists, where the known is surrounded by vast realms of the unknown. This might seem daunting, but it's also exhilarating. It means that no matter how much we learn, there will always be more to discover. No matter how far we see, there will always be invisible realms beyond our perception. The universe will never run out of mysteries, never cease to surprise us, never stop revealing new layers of reality that were always there but invisible until we developed the eyes to see them. The story of Three-Eye Atlas and the invisible population it represents is ultimately a story about the expansion of human awareness. We're learning to perceive things that were always there but hidden, to understand connections that were always real but invisible, to appreciate the richness of a universe that is far more complex and wonderful than we imagined. Each interstellar object we discover is not just a new data point, but a revelation, showing us that the cosmos is more alive, more dynamic, more interconnected than we knew. As you drift towards sleep tonight, surrounded by the invisible cosmic population we've been contemplating, remember that invisibility is not absence. The objects we cannot see are as real as those we can. The connections we cannot perceive are as strong as those we can measure. The universe is full of invisible wonders, hidden treasures, secret passages between stars. We're surrounded by cosmic mysteries, embraced by invisible threads that connect us to every star in the galaxy, accompanied by countless invisible wanderers on our journey through space. The darkness around us is not empty, but full, not silent, but whispering with cosmic secrets, not static, but alive with invisible motion. Every moment, objects from distant stars are passing through our solar system, most of them forever invisible, but all of them part of the grand cosmic dance. We're not alone in an empty universe, but surrounded by invisible companions, cosmic messengers that have been traveling for millions or billions of years to pass through our neighborhood at just this moment in cosmic history. The question, was Three-Eye Atlas always invisible until now, has led us through contemplations that have transformed our understanding of our cosmic environment. Yes, objects like Three-Eye Atlas have always been passing through our solar system, invisible to any observers who might have been watching. But more profoundly, we've discovered that invisibility is not a barrier, but an invitation. Not a limitation, but a promise of endless discovery. The invisible population around us is a reminder that the universe is far richer than we can perceive, far more wonderful than we can imagine, far more connected than we ever dreamed. And now, as our cosmic journey together draws to its close, as we prepare to release our consciousness into the embrace of sleep, let's hold in our awareness this final thought. We exist in a universe where most of what is real is invisible, where most of what happens occurs beyond our perception, where most of the connections that bind the cosmos together are too subtle for us to detect. Yet we're part of it all, made of the same stardust as the invisible wanderers, following our own cosmic trajectory through space and time. Briefly visible in the light of consciousness before returning to the cosmic mystery from which we emerged. The invisible population revealed by Three-Eye Atlas surrounds us like a cosmic ocean, vast and deep and mostly hidden, but real and present and eternal. We float in this ocean of invisible wanderers, each one carrying stories we'll never read, secrets we'll never know, connections we'll never fully understand. Yet knowing they're there transforms our experience of existence, adding depth and richness to every moment, connecting us to the vast cosmos in ways we're only beginning to appreciate. Sleep now, surrounded by invisible cosmic companions, embraced by threads of connection that stretch across the galaxy, accompanied by wanderers that have been traveling since before Earth existed. Rest in the knowledge that you're part of something vast and beautiful and mostly invisible, something that includes every star and every space between stars, every object we can see and the countless ones we cannot. Dream of the invisible population that surrounds us, the cosmic dance that continues whether we observe it or not, the eternal circulation of matter and information through the galaxy that makes us all cosmic citizens, all temporary gatherings of ancient wanderers, all part of the vast invisible tapestry of existence. The universe continues its patient processes as you rest. Invisible objects are entering our solar system. Others are leaving, still others are passing through the spaces between planets. All of them invisible but real. All of them part of the cosmic story. 3E, Atlas, continues its journey into the darkness, returning to invisibility but carrying with it the memory of its brief visibility, its moment in our sun's light, its contribution to our understanding of the cosmos. It will travel for millions more years, invisible but real. A cosmic wanderer that helped us see that we're surrounded by wonders we cannot see, connected by threads we cannot perceive, part of a universe that is mostly invisible but entirely magnificent, Tomorrow the sun will rise, and the visible world will return to your awareness. But perhaps you'll remember that beyond the blue sky, beyond the visible planets and stars, the invisible population continues its eternal dance. Perhaps you'll carry with you the knowledge that emptiness is fullness, that darkness is alive with invisible light, that isolation is connection through invisible threads. Perhaps the story of Three-Eye Atlas will have changed not just your understanding, but your experience of existing in a cosmos where most of what is real is invisible, most of what is important is hidden, and most of what connects us to the universe is too subtle to perceive, but absolutely real. The cosmic meditation we've shared tonight has been a journey from visibility to invisibility and back again, an exploration of what it means to exist in a universe where most of reality is hidden from our perception. We've discovered that our solar system is not isolated but constantly visited, not empty but full of invisible wanderers, not separate but connected to every other star system through the patient exchange of cosmic messengers. We've learned that Three-Eye Atlas was indeed always invisible until now, along with countless companions that remain invisible still, all of them part of the vast cosmic circulation that has been going on since the galaxy began. As consciousness gently releases its hold and you drift into the cosmic darkness of sleep, remember that you're surrounded by invisible wonders, accompanied by cosmic wanderers, connected to distant stars through threads you cannot see. The universe is so much richer than we knew, so much more alive than we imagined, so much more connected than we dreamed. And you're part of it all, a conscious observer briefly able to perceive a tiny fraction of the cosmic dance, a temporary arrangement of matter that has been travelling for billions of years and will continue travelling for billions more, a cosmic citizen in a universe where most of what exists is invisible, but absolutely, magnificently, eternally real. Rest now in the cosmic darkness, surrounded by invisible companions, embraced by connections you cannot see, part of a universe that is mostly hidden, but entirely present. The invisible population continues its dance around you, through you, within you. You're made of cosmic wanderers temporarily gathered. You're surrounded by cosmic wanderers eternally travelling. You're part of a cosmic dance that is mostly invisible, but completely real. Sleep peacefully in this cosmic truth, this vast invisible embrace, this eternal dance of matter and energy, information and connection, visibility and invisibility, knowledge and mystery. The story of Three-Eye Atlas has shown us that we live in a universe of infinite depth, where every answer reveals new questions, where every discovery shows us how much more there is to discover, where every visible object hints at countless invisible ones. This is not a cause for frustration, but for wonder, not a limitation but a promise. The universe will never run out of mysteries for us to explore, never cease to surprise us with hidden wonders, never stop revealing new layers of invisible reality. We're at the beginning of an endless journey of discovery, where each revelation about the invisible population around us opens new vistas of cosmic understanding. And so, as our contemplation comes to its gentle close, as you settle into the deepest rest, know that the cosmic story continues. Invisible objects are passing through our solar system at this very moment. The universe is whispering its secrets in languages we're only beginning to hear. The cosmic dance goes on, mostly invisible but entirely real, mostly hidden but absolutely present, mostly unknown but infinitely knowable, for those who learn how to look beyond the visible into the vast invisible reality that surrounds us all. Good night, cosmic traveller. Sleep well, surrounded by invisible wonders. Dream of the vast population of cosmic wanderers that share our space, our time, our journey through the universe. And remember, when you wake, that you've glimpsed tonight something profound about the nature of reality, that most of what exists is invisible, most of what is real is hidden, and most of what connects us to the cosmos is too subtle to see but absolutely, eternally, magnificently there. The universe is so much more than what we can see, and you're part of it all. Visible and invisible, known and unknown, a conscious witness to the vast cosmic dance that continues forever, whether we watch or not, whether we know or not, whether we see or not.